Swayam Prabha. Digital India. Educated India.
Okay, hello friends. So, in the last class we have discussed regarding the different components of digital relays, and we have discussed that there are different components available in digital or numerical relay. So, we have seen the block diagram of digital and numerical relay, and we have seen that there are various components like the signal conditioning block is there, then conversion subsystem block is there, then digital input and digital output modules are also there, algorithm module is also there, and along with this various communication peripheral devices and the human machine interface block is also there. So, and we have also discussed the importance of each and every component, why those components are required, that also we have discussed. Now, in the today's class we will discuss about the sampling. So, whenever we carry out the sampling, what are the different rules we need to consider. Then we will also discuss the concept of aliasing. So, if sampling is not proper, then what are the different errors that is to be introduced in the original or reconstructed signal. So, that also we will discuss, and at last we will discuss what are the factors that is to be considered for sampling rate, and we will also discuss the concept of sliding window. So, let us start with the first, what is sampling. So, we know that the voltage and current are continuous signals. So, as I explained you in the last slide, when we have a feeder and when we are going to acquire the signals of let us say current from the secondary of the CT, this is our CT. So, then this current signals phase wise, these signals are given or acquired by the data acquisition system, and these signals are given to the analog to digital converter block. So, the function of analog to digital converter block is to convert analog signals which are acquired through CT secondary and PT secondary or CVT secondary into digital form. Now, whenever ADC is going to acquire the voltage or current or any other signals, then there must be some rule regarding the sampling frequency. So, selection of sampling frequency plays an important role during data acquired from CT or PT secondary or both. So, let us consider, let us assume that we have the F0 is the fundamental frequency of analog signal, let us say the current signal which we acquired from secondary of CT, and that is given to ADC. Fs be the sampling frequency, that means Fs is the frequency at which ADC is going to sample the data, and Fmax is the maximum frequency component present in the acquired signal. These three are the points which we consider. Then as per Nyquist criteria, sampling frequency of the acquired signal should be always greater than 2 times the maximum frequency component present in the acquired signal. So, the periodic signal can only be reconstructed only and only if your sampling frequency is greater than 2 times the highest frequency component present in the signal. This is nothing but the Nyquist criteria, and mathematically equation wise we can represent this using this equation. Let us say this is equation number 1, where Fs is the sampling frequency of the acquired signal at which we are going to sample, and F max is the maximum frequency component present in the acquired signal. Let us say we have a signal whose fundamental frequency, let us say F0 is the fundamental frequency of the signal which we are going to acquire, let us say it is 50 hertz, and the sampling frequency which we are going to sample the signal, let us say Fs, that is 300 hertz. So, with this available data of fundamental frequency F0, that is 50 hertz, and Fs, that is 300 hertz, we can definitely find out number of samples required for a periodic signal in a cycle. So, in one cycle how many number of samples are there we need to acquire, or ADC has to acquire, that we can find out if these two values are known, that is F0 and Fs. Then how we can calculate? We can calculate using the equation n, which is nothing but the number of samples per cycle, that is equal to the sampling frequency divided by the fundamental frequency. So, if we do that, then if we put these values we will get the 6 samples. So, you can see here in the waveform, this is the first sample, this is the second sample, this is the third sample, this is the fourth sample, this is the fifth sample, and this is sixth sample. So, in one cycle here you can see, in one cycle we are going to acquire 6 samples, and this is how we are going to acquire. Now, here you can see that your fundamental frequency F0, this is normally constant, maybe either in our Indian system 50 hertz or maybe some other countries 60 hertz. However, only variable thing or parameter is the sampling frequency, and that we can vary. If we vary the sampling frequency, then number of samples which we need to acquire in a cycle, that may vary. So, it can be 6, or it can be higher value also, or it can be lower value also. Now, let us consider a case where sampling frequency Fs, at which we are going to acquire the signal, is not going to follow the Nyquist criteria or Nyquist rule. So, Fs is, let us say, lower than or equal to 2 times the maximum frequency present in the acquired signal. If this is the case, then it is going to lead these 3 effects. The first effect is known as aliasing effect, the second effect is known as same output, and third effect is known as folding phenomena. So, let us consider each and every effect in detail one by one. So, now let us see what is aliasing. So, to understand the aliasing effect, let us consider one example of a signal who has 50 hertz fundamental frequency. So, your F0 is 50 hertz, and this signal is sampled at a sampling frequency of 200 hertz, and maximum frequency component present in this signal is, let us say, 250 hertz. So, according to Nyquist criteria, your Fs, which is 200 hertz, in this case this is 200 hertz, that is lower than 2 times the F max is 250 hertz. So, 2 times F max, that is 500 hertz. So, 200 hertz is lower than 500 hertz. So, Nyquist rule or criteria is not followed, and it may lead to the 3 different effects as I told you. Now, to understand the aliasing in more details, let us consider a signal x t, which is given by 2 terms. The first term, that is 5 sin omega 0 t, where omega 0 t is nothing but 2 pi f 0 t, f 0 is the fundamental frequency, and the second part that contains 5 sin 5 omega 0 t. So, if I plot this x t signal which contains 2 parts 1 and 2, one is 5 sin omega 0 t and other is 5 sin 5 omega 0 t, then this signals looks like this, where on x axis we have the time in millisecond and on y axis you have the amplitude. Let us say we are acquiring current quantity, so let us say ampere. So, this signal x t looks like this. Now, if I plot only the first part of this signal x t, that is 5 sin omega 0 t, then this looks like this, and you can see that you have time on x axis. So, in one cycle, that is 20 millisecond, we can see here this is one cycle, it will have only one sinusoidal signal, right, and its amplitude is, that is 5. Now, if I plot second part of x t, then second part of x t looks like this, that is 5 sin 5 omega 0 t. So, again you can see on x axis you have 5 sinusoidal waves are available in 20 millisecond, compared to earlier case you have only one sinusoidal wave in 20 millisecond, right. Moreover, amplitude is also 5, and if I combined both part 1 and part 2 of x t, then you will have the signal which looks like this. Now, if I consider, let us say we are sampling at 4 samples per cycle. So, as I told you, my f 0 is 50 hertz and my sampling frequency, we are sampling the this signal at f s is equal to 200 hertz, which is not going to follow the Nyquist criteria. So, if I take 200 by 50, then you will have number of samples in one cycle. So, that comes out to be 4. So, on time axis, as I told you, we have 20 millisecond. So, we can say that for 4 samples in a cycle, if we have 20 millisecond, then for one sample we have obviously 5 millisecond. So, at every 5 millisecond we have to acquire the sample, and total sample we have to acquire are 4 in one cycle. So, if I just tell you the original signal x t, right, this is our signal x t. So, if I tell you this signal we are going to acquire 4 samples at every 5 millisecond, then this is your first sample, this one. The second sample is acquired at 5 millisecond, the third at 10 millisecond and fourth at 15 millisecond. So, this is going to complete your number of samples in a cycle, that is 4. So, obviously, we are going to acquire these samples one by one, and whenever this is the next sample, when it is available, again another 4 samples, again another 4 samples, like this. Now, you can see that if I plot both the parts of x t together, the first term, that is 5 sin omega 0 t, and second part you can see that is 5 sin 5 omega 0 t, then this both are superimposed together and it looks like this. So, this is your red color is your first part and blue color is your second part of our signal x t. So, you can see that here I have shown both the parts of x t, along with I have also shown the sampling instant. This is your first sample, second, third and fourth, and again next sample. This is your next sample. So, you can observe from these two diagrams with sampling instances that the fifth harmonic component, that is this blue one, that will take an alias of the fundamental component. So, that means that is going to hide behind the fundamental component. So, if I consider the same signal, red one, your first part 5 sin omega 0 t, and second blue one, second part 5 sin 5 omega 0 t, then we can say that your fifth harmonic component will take an alias of the fundamental component. So, you will see that you will find like this. and when you reconstruct the original signal from your whatever available samples in digital form, then it will give you the fundamental component only with double amplitude. So, you can see that amplitude of this, that is 10, whereas our original signal again you can see its amplitude is 5 only. So, we can say that when we are going to reconstruct the signal in which Nyquist rule is not followed, that means your sampling frequency is not greater than 2 times f max. If this rule is not followed, then we will observe aliasing effect, and whatever is the fifth harmonic in this case, that is going to take an alias of the fundamental component. Now, second effect let us discuss, that is known as same output. So, as the name suggests, same output means at every time we are going to have similar output, same value. This is happened when your sampling frequency is equal to or integer multiple of analog signal frequency, then your acquired signals will have the similar output. So, to understand this, let us consider another signal x t, that is given by sin 2 pi 250 t, and this signal let us assume that it is sampled at fs is equal to 500 hertz. You can see that here the f max, that is the maximum frequency component present in this signal x t, that is 250 hertz. So, according to Nyquist criteria, your sampling frequency should be greater than 2 times f max. However, here we have fs that is same as 2 times f max, because your fs is 500 hertz and f max is 250. So, 2 times f max, that is also 500 hertz. So, if this is the case, then you can see from this waveform you will have the 0 value for all samples whatever you are going to acquire. So, this is also an important phenomena, and that is why we need to consider this Nyquist criteria while selecting the sampling frequency of the acquired signal. Now, the third important effect is known as folding phenomena. So, folding phenomena is nothing but overlapping of frequency spectra. So, this is going to happen when your sampling frequency is lower or equal to 2 times the maximum frequency component present in the acquired signal. So, in this case, to understand the folding phenomena, let us consider the x t one signal which is given by sin 2 pi 50 t plus sin 2 pi 150 t. So, x t contains two parts, the one part you have sin 2 pi 50 t and second part you have sin 2 pi 150 t. And let us assume three different sampling frequencies, that this signal x t is going to acquired at three different sampling frequency. The first, it is let us say 200 hertz sampling frequency, second let us say it is 300 hertz, and third let us say it is going to acquire at 400 hertz. Now, if we consider the same x t which is acquired at 200 hertz sampling frequency, so fs is 200 hertz, then if I consider the x t, then you can see that we can start from this 0 part here, okay, and then we have the component 150. So, you can go from this, let us say up to 150. So, you can see 0, 50, 100 and 150. So, on both the side you can go up to 150. Then the next part you can see your sampling frequency is 200 hertz. So, I have marked here 200 hertz. So, another line is again at 200 hertz, and from 200 hertz you have to go both the sides minus 150. So, 200 minus 150, it will be available here 50, and on this side 200 plus 150, that is 350. So, you can see there is an overlapping of this. Let us say we sampled this signal x t, which has two components sin 2 pi 50 t and sin 2 pi 150 t at sampling frequency, that is 300 hertz. So, in that case you have the first part here and you have the 150 on this side and another 150 on this side, and when you write the sampling frequency here, that is 300 hertz, then you can plot on both the sides again 150 and again 150. So, 150 and 450. So, then you will have this point. So, you will get same output, second type of error. And third, if we acquire this same x t signal at f s is equal to 400 hertz. So, here the Nyquist criteria is followed, then you can see there is no overlapping here, right. So, you can start from this 0 and you can go both the side 150 and then again you have from 0 to 400 here. So, again 400 minus 150, that is 250, and 400 plus 150, that is 550. So, there is no overlapping here, right, you can see here and here. So, this is nothing but the folding phenomena. Now, let us see when we are going to select the sampling rate, that is what are the number of samples in a cycle we need to have or consider, then we need to consider three important factors. So, while deciding how many number of cycles I have, means let us say we are acquiring one current signal. So, then whether we will go for 6 samples in one cycle or 12 samples or 20 samples or 40 samples in a cycle, that is decided by these three important factors. These factors are: the first, time available for computation, the second is the computational requirement, and third, that is the reconstruction of signal. So, let us discuss each factor one by one. The first factor is the time available for computation. So, here I have shown 4 graphs, and in each graph you can see I have used 4 samples per cycle in first graph. In second graph I have used 8 samples per cycle. In third graph I have used 16 samples per cycle, and in fourth graph I have used 32 samples per cycle. So, I have doubled the number of samples in a cycle from 4 to 8, 8 to 16 and 16 to 32. So, here you can see that when I have 4 samples per cycle in the first graph, we have to acquire the samples at this point, right, 3, 4, and then this is your next sample. Okay. Similarly, when you have 8 samples, that means when you have 4 samples in a cycle, you have to acquire the sample at every 5 millisecond. When you have second graph, when you have 8 samples in a cycle, then you have to start here and you have to end here 1 to 8, right. So, first, second, third, like that. So, you have to acquire the sample in the second graph at every 2.5 millisecond. This time further reduces if you go the third waveform, where you have 16 samples you have to acquire, and at each at 1.25 millisecond, and in fourth graph you have to acquire 32 samples each at 0.625 millisecond. So, you can see that higher the number of samples in a cycle you acquire, lesser will be the computation time available between 2 consecutive samples, and this is very important point. The second is the computational requirement. So, again same 4 graph I have shown, right, 1, 2, 3 and 4, and in 1, 2, 3 and 4 we have only difference is the number of samples in a cycle 4, 8, 16 and 32 in graph number 1, 2, 3, 4. So, as you increase the number of samples in a cycle, then whatever mathematical operations you need to perform to calculate a particular quantity which is required by the algorithm, let us say RMS value or some phasor value or any other thing, that is also going to increase. And at the same time, as you increase the number of samples in a cycle, accuracy is also going to increase. In one case where 4 samples per cycle is there, accuracy is lowest, and in fourth case where number of samples in a cycles are 32, where the accuracy is the highest, but the mathematical operations required to calculate the RMS value that increases, and the time between each sample, that is also very small, that is 0.625 millisecond compared to first graph where you have 5 millisecond. The third thing, that is the reconstruction of signal. So, again you can see this is your first, second, third and fourth graph, where you have 4 samples, you have 8 samples, you have 16 samples and you have 32 samples. So, here you can see that when you reconstruct the signal, this signal is not sinusoidal wave, this 8 samples is also not perfectly sinusoidal, 16 you will find few deviations at few points, but 32 it looks like perfect sinusoidal. So, higher the sampling rate provides better reconstruction of the signal, that we can see. So, as we increase the number of samples in a cycle, then reconstruction is better. However, if we have higher number of samples in a cycle, then it also increases computational complexity. So, higher sampling rate, however, it is required when high frequency noise exists in the acquired signal. So, when we select the sampling rate, we have to consider the 3 important parameters which we have discussed. However, as accuracy and computational requirement both are contradictory in nature, so it is the duty of protection engineer to have a balance or maintain a balance among these two things. For all protection applications, normally it requires low sampling rate compared to the control and measurement application. Most of the standard relay manufacturers, they use 8 samples to 64 samples in a cycle. So, they will give the range 8, 16, 32, 64. However, as per IEC 61850, that is substation and automation protocols, for protection applications 80 samples per cycle is standard, whereas for power quality applications 250 samples per cycle is also standard. Now, let us see the sliding or moving window concept. So, when we consider the sliding or moving window concept, let us first consider one simple wave where I am going to acquire the sample at some fixed time interval. So, fixed time interval between two consecutive samples play an important role, and this fixed time interval between two consecutive samples, that is known as sampling interval. So, here this is my first sample, this is second, third, fourth, fifth and so on. So, you can see the interval between first and second, that is also Ts, between second and third, that is also Ts and so on. So, that is fixed. How do you obtain the sampling interval Ts? It is simply reciprocal of sampling frequency Fs. Now, when we consider the sampling and quantization, then two approaches are normally used. The first is you can see this waveform, where you can acquire the sample at every sampling interval. So, this is second, third, when you acquire the sample, you acquire the sample and whatever necessary computation you performed before the next sample is available or acquired. So, this is one approach. The second approach is you acquire a set of samples, let us say this window is given. So, you acquire let us say 1, 2, 3, 4, 5, 6, 7, 8 samples, let us say set of samples, let us say 8, store them in buffer and thereafter you perform the computation by the algorithm, right, depending upon the logic, and then you acquire next set of samples, let us say that is also 8. Another approach is also possible. Now, the concept of sliding or moving window. So, here you can see that what is data window or moving window or sliding window. So, data window is nothing but a group of acquired samples where you need to perform some computation or estimation. So, here you can see I have shown this data window 1 which contains 3 samples, let us say 1, 2 and 3. Similarly, you can see another data window that also contains 3 samples, data window 3 that also contains 3 samples. So, in each data window number of samples that remain constant. So, if I consider this, you can see there are 3 samples. Now, whenever next window I considered, let us say this, then you see this sample is discarded and this sample is again moved into the data window. So, you can see again I repeat 3 samples. When I take next window, then number of samples in a window that remains constant, that is 3 here. However, this sample is discarded and this is included. Similarly, if I go further, then this sample is discarded and this is included, like that you can proceed further. So, whenever new sample is available, the previous sample is discarded and the next sample is included, but keep in mind number of samples in a window that remain always constant. Now, if I consider a window with size of let us say 1 cycle, here 2 cycles are shown, but let us say 1 cycle. So, then you can see this is one data window that contains the let us say samples from first, second, third, fourth, fifth, sixth, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. So, 16 samples we have considered in one window. So, in one cycle we have considered 16 samples are available. So, when I take next samples, the first sample is discarded and the next sample 17th sample that is included, right. Similarly, when you further go, then 18 number sample is included and second number sample that is discarded. So, this window is moving or sliding. So, that is why this is known as sliding or moving window concept. So, in this lecture we started our discussion with the sampling and we have discussed that we have to follow the Nyquist criteria, that is sampling frequency should be greater than the 2 times the maximum frequency present in the acquired signal. If it is not followed, then 3 important effects are observed. The first is the aliasing, second is the same output and third is the folding. Then we have discussed the concept of data window and along with that we have also discussed the sliding window concept. And with the sampling we have discussed what are the factors to be considered when we decide the sampling rate. Thank you.